Hello everyone. Today we are going to analyze this beam using flexibility matrix method. Before analyzing, let us see the beam one time. In this beam, there are two spans, span AB and span BC. In the span AB, there is a point load 24 kN. It is acting in the center. In the span BC also, there is a point load 12 kN. It is also acting in the center. The moment of inertia for the span AB is I. For the span BC, it is 2I. Length of the span AB is 10 meter. Length of the span BC also is 10 meter. In the point A, there is a fixed support. In the points B and C, there are hinged supports. The support in the point B sinks by 10 mm. The support in the point C sinks by 6 mm. The Young's modulus E is given as 12 kN per millimeter square and the moment of inertia is given as 125 into 10 power 7 millimeter power 4. The moment of inertia I is given in millimeter power 4. So we have to convert it into meter power 4. We know that 1 millimeter is 1 upon 1000 meter, but here we have power 4. So we have to divide this value by 1000 power 4. Finally, we are getting the moment of inertia in meter power 4. The Young's modulus E is given as 12 kN per millimeter square. We have to convert this value into kilonewton per meter square. Here we have mm square, so we have to divide by 1000 square. When we do that, we are getting in kilonewton per meter square. For our own convenience, let us multiply the moment of inertia and Young's modulus. When we do that, we are getting 15,000 kilonewton meter square. The settlement at B is given as 10 millimeter. Let us divide 10 by 1000 so that we will get 0.01 meter. In the same way, let us convert the settlement at C. When we divide 6 by 1000, we will get 0.006 meter. Now let us find the degree of static indeterminacy. In this beam, the number of unknown reactions and moments is 4. They are MA, RA, RB and RC. The available equilibrium equations are 2. Sigma m is equal to 0 and sigma v is equal to 0. The degree of static indeterminacy is equal to 4 minus 2. We will get 2. In this beam, the supports B and C are sinking. So we have to release RB and RC. When we remove the supports from the point B and from the point C, this continuous beam becomes a cantilever beam. This beam is called the released structure. We have made the released structure. Now let us make the coordinates diagram. In this analysis, we have two coordinates. The first coordinate is in the point B and the second coordinate is in the point C, because in these points only we have removed the supports. Let us see the formula to find the reactions. P matrix is equal to delta matrix inverse into delta matrix minus delta L matrix. Inside the P matrix, delta L matrix and delta matrix, there will be two values because in this analysis we have two coordinates. Since we have two coordinates, the size of the flexibility matrix will be 2 cross 2. Inside the P matrix, we will have the reactions RB and RC because these are the reactions we have removed. In this formula, now let us find the delta matrix. We know that inside the delta matrix, we will have the final displacements. Our first coordinate is in the point B. In the point B, the support sinks by 0.01 millimeter. The sinking occurs always downwards, so we have to apply this value with the negative sign. Our second coordinate is in the point C. The support in the point C sinks by 0.006 millimeter. Since the sinking occurs downwards, we have to apply this value with the negative sign. In this formula, now we are going to find delta L matrix and the flexibility matrix. To find these two matrices, I am going to apply unit load method. Here we have to find the moments in 3 times. We have to find M, M1 and M2. Using the loads given in the question, we have to find the moment M. To find M1, we have to apply unit load in the first coordinate. Our first coordinate is in the point B. In the point B, I have applied unit load. And then we have to find the moment. To find the moment M2, we have to apply unit load in the second coordinate. Our second coordinate is in the point C, so I have applied unit load. Then we have to find the moment. We have to be very careful. When we find M1 and M2, we should not consider the loads. We have to remove them. In this beam, let us make two more points. Under the point load 12 kN, let us make the point D. Under the point 24 kN, let us make the point E. Before finding the moments, let us make sections. In this beam, there are 4 different parts: CD, DB, BE and EA. So we have to make 4 sections. You can see that I have made the first section in CD, the second section in DB, the third section in BE, and the fourth section in EA. Before finding the moments, let us make the free body diagram. When we make the free body diagram, it is very easy to find the moments. Let us split the beam into two parts from the point B because it is the joint. When we do that, we are having two different parts, AB and BC. Let us consider the span BC. In the span BC, in the point D, there is a point load 12 kN. Because of this load, a reaction 12 kN is developed in the point B. Since this load is acting downwards, the reaction should be acting upwards. Let us find the moment in the point B. This load is acting in the clockwise direction and the distance is 5 meter. 12 into 5, we will get 60. Since this load is acting in the clockwise direction, the developed moment should be acting in the anti-clockwise direction. Now let us consider AB. On the right side, in the point B, the moment is acting in the anti-clockwise direction. So, in the left side, it should be acting in the clockwise direction. On the right side, the reaction is acting upwards. So, in the left side, it should be acting downwards. Now, let us take BC and find the moments in the sections. In BC, we have made two sections. The first section in CD, the second section in DB. I have made both of the sections at a distance of x from the point C. For the span BC, the moment of inertia is 2I, so the flexural rigidity for CD and DB should be 2EI. Both of these sections are starting from the point C, so the origin of CD and DB should be C. The limit for CD is 0 to 5. The limit for DB is 5 to 10. Now let us find the moment M. First, let us find it in CD. In CD, up to the section, there is no load, so the moment M will be 0. Now let us find the moment in DB. We are finding the moment about the sections from the point C. In this case, we are moving towards left hand side. Clockwise will be negative and anti-clockwise will be positive. Up to the section, we have only one load, that is the point load 12 kN. This load is acting in the clockwise direction, so it will be negative. For the distance, we have to take this distance. This distance is x minus 5. Let us multiply minus 12 with x minus 5. When we do that, we are getting minus 12x plus 60. Now let us take the portion AB. In AB, we have made two sections. The third section in BE and the fourth section in EA. I have made both of the sections at a distance of x from the point B. So the origin for BE and EA should be B. The moment of inertia for the span AB is I. So the flexural rigidity for BE and EA should be EI. The limit for BE is 0 to 5. The limit for EA is 5 to 10. Now let us find M in BE. Up to the section, we have a point load 12 and the moment 60. The point load is acting in the clockwise direction, so it will be negative, and the distance is x, so minus 12x. The moment is also acting in the clockwise direction, so it is also negative. Now let us find the moment in EA. Up to the section, we have the point loads 12 and 24 and the moment 60. The point load 12 is acting in the clockwise direction, so it will be negative, and the distance is x, so minus 12x. This movement is acting in the clockwise direction, so it is also negative. The point load 24 is also acting in the clockwise direction, so it is also negative. For the distance, we have to take this distance. This distance is x minus 5. Then we can multiply minus 24 with the x minus 5. When we do that, we will get this. After we can make the simplifications. After the simplifications, we are getting this. Let us apply that here. We have found the moment m. Now we are going to find the moment m1. For that, we have to apply the unit load in the first coordinate. Then we can make the free body diagram. Let us assume that the unit load is applied just left of B, so no need to consider the right side part. Now let us find M1 for CD. Up to the section there is no load, so M1 will be 0. Now let us find M1 for DB. Here also up to the section there is no load, so M1 for DB is also 0. Now let us find M1 for BE. Up to the section we have only one load, that is the unit load. This load is acting in the anti-clockwise direction, so it will be positive and the distance is x. 1 into x, we will get x. Now let us find M1 in EA. Here also up to the section we have only one load, that is the unit load. This load is acting in the anti-clockwise direction, so it will be positive and the distance is x. 1 into x, we will get x. Now we are going to find the moment m2. For that we have to apply unit load in the second coordinate. Let us make the free body diagram. Because of this unit load, a reaction is created in the point B. This load is acting upwards, so the reaction should be acting downwards. Now let us find the moment in the point B. This load is acting in the anti-clockwise direction and the distance is 10 meter. 1 into 10, we will get 10. Since the load is acting in the anti-clockwise direction, the developed moment should be acting in the clockwise direction. Now let us take the left side. On the right side in the point B, the moment is acting in the clockwise direction. So in the left side, it should be acting in the anti-clockwise direction. On the right side, the unit load is acting downwards. So on the left side, it should be acting upwards. Now let us find M2 in CD. In CD, the unit load is acting in the anti-clockwise direction. So it will be positive and the distance is x. 1 into x, we will get x. Now let us find M2 in dB. The unit load is acting in the anti-clockwise direction, so it will be positive and the distance is x. 1 into x, we will get x. Now let us find M2 in BE. The unit load is acting in the anti-clockwise direction, so it will be positive and the distance is x. 1 into x, we will get x. The moment is acting in the anti-clockwise direction, so it is also positive. Now let us find M2 in EA. The unit load is acting in the anti-clockwise direction, so it will be positive and the distance is x. 1 into x, we will get x. The moment is also acting in the anti-clockwise direction, so it is also positive. In this formula, now let us find delta L matrix. In delta L matrix, first let us find delta 1L. The formula to find delta 1L is integration of m1 upon ei dx. For CD, the value of m and m1 are 0. So 0 into 0, we will get 0. For dB, the value of m1 is 0. So when we multiply 0 with this value, we will get 0. So for CD and dB, no need to make the integration. We can straight away put 0. So for CD and dB, no need to make the integration. We can straight away put 0. For BE, the limit is 0 to 5. For EA, the limit is 5 to 10. From BE, let us apply the values of m and m1 in the integration. Also from EA, let us apply the values of m and m1 in the integration. The value of EA is 15,000 kilonewton meter square. Let us apply that also. Then we have to use the calculator and do the integrations. If you do not know how to use calculator for the integrations, see the description below. There is a link. You can click the link and watch the video. I have used the calculator and got these values. Let us add these two values. After adding, we are getting minus 19 upon 30. In the delta L matrix, now let us find delta 2L. The formula is integration of m2 upon ei dx. For CD, the value of m is 0. When we multiply 0 with the x, we will get 0. So no need to make the integration. For dB, the limit is 5 to 10. For dB, the flexural rigidity is 2ei. So we have to multiply the ei value with 2. In the integrations, let us apply the values of m and m2. Now let us use the calculator and get these three values. Let us add these three values. After adding, we are getting minus 1.675. In the delta L matrix, we have found delta 1L and delta 2L. Let us apply the values. In this formula, now we are going to find the flexibility matrix. In this matrix, first let us find delta 1,1. The formula is integration of m1 square upon ei dx. For CD and dB, the value of m1 is 0. So no need to make the integration. From BE and EA, let us apply the values of m1. After the calculation, for delta 1,1, we are getting 1 upon 45. In the flexibility matrix, now let us find delta 1,2 and delta 2,1. Both of them having the same formula, integration of m1 m2 upon ei dx. For CD and dB, the value of m1 is 0, so no need to make the integration. From BE and EA, let us apply the values of m1 and m2. After the calculation, we are getting delta 1,2 and delta 2,1, which is equal to 1 upon 18. In this matrix, now let us find delta 2,2. The formula is integration of m2 square upon ei dx. In CD, first time we have a value. For CD, the limit is 0 to 5. The flexural rigidity is 2ei. So we have to multiply the value of ei with 2. In the integrations, let us apply the values of m2. After the integrations, we have to add these four values. After adding, we are getting 1 upon 6. In the flexibility matrix, we have found all of the values. Let us apply them. In this formula, we have found everything. Let us apply them. We can add these two matrices. After adding, we are getting this. For this matrix, we have to find the inverse. We can apply all of the values in the calculator and get the inverse. If you do not know how to find the inverse in the calculator, see the description below. There is a link. You can click the link and watch the video. I have used the calculator and got the inverse. Now we have to multiply these two matrices. After multiplying, we are getting RB and RC. For RB, we are getting 18.09 kilonewton. For RC, we are getting 3.984 kilonewton. Now let us apply the rule. Sigma V is 0 and find out RA. RA, RB and RC are acting upwards, so all three of them will be positive. The point loads 24 kN and 12 kN are acting downwards, so they will be negative. In this way, we can calculate RA, which is equal to 13.926 kN. Now let us find MB. I am going to find the moment in the point B from the point C. In this case, I am moving towards left hand side. Clockwise will be negative and anti-clockwise will be positive. RC is acting in the anti-clockwise direction, so it will be positive and the distance is 10. So RC into 10. The point load is acting in the clockwise direction, so it will be negative and the distance is 5. So minus 12 into 5. Finally, we are getting MB, which is equal to minus 20.16 kilonewton meter. Now let us find the moment in the point A, MA. RC is acting in the anti-clockwise direction, so it will be positive and the distance is 20. The point load is acting towards the point A in the clockwise direction, so it will be negative and the distance is 15. RB is acting towards the point A in the anti-clockwise direction, so it will be positive and the distance is 10. The point load is acting in the clockwise direction, so it will be negative and the distance is 5. After the calculation, we are getting MA, which is equal to minus 39.42 kilonewton meter. In this analysis, we have calculated both of the moments MA and MB. In the point C, there will be no movement because it is a simply supported end. Now, using the loads and reactions, we can make the shear force diagram. Now let us make the free movement diagram. For that we have to assume every span as a separate simply supported beam. Then we can use these formulas and draw these diagrams. Then using the end moments we can make end moment diagram. Then we can combine both of the diagrams so that we will get the bending moment diagram. Now we are going to end this session. Thank you for watching this video.